too laid back, right? That's like weekend. Okay, well, welcome everybody. Can people on Zoom hear me okay? I don't know if I can actually see the chat. Okay, so if you can't hear, send something in the chat and Amin will deal with it. Okay, so assignment 2 I'm going to release soon. So how did assignment 1 go? Too easy? Too hard? Really? Too easy, too hard, just right? How many thought it was just right? Few. How many thought it was too hard? Few. Too easy? Anybody thought? No, Amin thinks it's too easy. Okay, wait till he marks it. What made it hard? Was it like just like yeah?
It was easy to get a first implementation down. It was hard to get a really optimal solution, like getting the throughput as maximal as possible.
Okay. One thing to remember, so that's useful to know, you don't have to get a perfect answer, right? Like, so we kind of give a little bit for further optimization, but it's not like some kind of binary function, right? Of like, oh, you didn't optimize it to the nth degree, therefore it's terrible. So bear that in mind in this next one. So I'll release assignment 2, should come out tonight. And I'll make it due approximately Wednesday, November 1st. I have to think about if I make it due on a Wednesday, whether everybody will just skip class. So I'm going to poll a few people to go, like, is this like a disastrous strategy, or should it be Thursday or what? It's related to assignment 1. So you're going to use Quartus again. So if you know Quartus now, that's great. You're going to optimize a somewhat more, not super complicated, but a more complicated computation of 2D convolution on FPGAs. This one is a little more variation in how much throughput you can get, so I'll give a prize for the highest throughput, mostly fame, but also an Amazon gift card. If you work it out, dollars per hour, probably not a good trade-off, okay? So it's not gonna be like a giant Amazon gift card, so don't go, I gotta do this because it's like, it's gonna make me rich. It's not. You probably would be better off going and spending your time elsewhere. And you're gonna rigorously compare, we've been talking about how do CPUs and GPUs work at a high level? How do we compare to them? We'll talk about that a little bit more in the first paper today. So we want you to do a rigorous comparison, but we don't want you to waste your time coding the CPU and GPU implementations because there are other courses for that. So we'll give you those. We just want you to analyze their behavior and summarize the comparison accurately. And you're gonna compare basically performance, so throughput, throughput per watt, and throughput per unit of area, which is a proxy for throughput per dollar, right? That's the main cost of chips. Okay, so I'm going to tell you a little bit about this assignment, which you haven't seen yet, but a little bit of background that hopefully makes it more understandable. Okay, so digital convolution is a key operation. So 1D convolution is a finite impulse response filter. So I've been talking about signal processing, really important in FPGAs. So this is a key building block of filtering and lots of the communication systems you see around. I'm not going to walk through this equation in detail, but it's just basically the discrete version of the convolution equation that you studied in undergrad. So if I want to do a low-pass filter, remember that in the time domain, a low-pass filter looks like this. It's a sinc function. We don't usually implement filters using analog components anymore, at least not at high speeds. So instead, you usually sample that function. So we get discrete points, as I've shown over here. And you take those discrete points in time. So these now turn into like sample numbers, like numbers from a sequence. And you take each of these values, multiply it by a coefficient, add it up, and you have the discrete version of a one-dimensional convolution, also known as a finite impulse response filter. It's finite because you basically don't keep going to infinity. This keeps going out to infinity, but you stop at some sample number and just say, I don't care about the remaining really small coefficients that might be out there. I approximate my filter. Yeah?
You mentioned this isn't done in analog anymore, but especially for high frequencies. But wouldn't you exactly want analog for high frequencies?
Well, so I'm not an analog designer, so I guess I'm the wrong person to ask super detailed questions about it. But the general trend nowadays is to do all your complicated processing in digital as fast as you can, because digital has scaled better than analog. So that's the general rule. Now there are exceptions to that. People doing extremely low power who say, I can handle it. I'm going to try to do it in analog because analog can be low power compared to converting everything to digital. So your modulation, like if you take a wireless communication system, there's a final stage where you're going to modulate it onto a carrier wave and send it out through your radio frequency system. Okay, that final modulation is going to be done like analog, right? There's some power electronics to do it. When a signal comes back off the antenna, you're going to demodulate it. So you basically multiply it by a signal to try to get it down to a lower frequency. That again is going to be done analog, typically. But after that, you usually digitize it right away. So you can move into the digital domain, do much more complicated signal processing at a much higher, well, I guess it's easier to design, especially if you need to carry quite a few bits of precision around. Does that make sense? So that's one-dimensional convolution. And that would be actually a very useful exercise as well. FPGAs are used a lot for one-dimensional convolution. They're also used a lot for two-dimensional convolution. And to make things a little more interesting, we're going to do the 2D version. So 2D convolution is the same idea. It's just your data is not organized as a sequence in time. It's organized as a grid, an XY grid. And this is used a lot for image processing. So if this grid represented an image, so it's pixels, we can slide a convolution window across it. So that convolution window, depending on what coefficients we put at every one of these spots that we're multiplying it by, we could make a low-pass filter in 2 dimensions. We could make a high-pass filter or an edge detector. So we could have a sharpening filter. We could have a blurring filter. We could have something that detects horizontal lines, something that detects vertical lines, etc. It basically is just a function of what coefficients we put in for these 9 values that we're going to slide along and convolve. So the way this works is let's say I take a 3x3 convolution, okay? I place that 3x3 convolution on part of my input data, my image, and I can do 9 multiplies and 8 adds, and I can get out a single output pixel. Now notice that I actually need to do a little bit of padding here. For a 3x3 convolution, it's actually going to go outside my image at this point. So if I center the convolution here, I need to consider there to be zeros around my image in order to apply this convolution filter or convolution window. Does that make sense? We're going to do this in a streaming style, which is pretty typical of FPGAs. So we're not going to give you a big array or a big RAM that has this image data in it. We're going to stream it in. Okay, so you're going to get sent this data, one value at a time, basically, and you're going to have to organize it. You should try to reuse it so that you get all the data you need to compute an output. So you need to buffer up enough data to compute this first value. And what I've shown in green here is the data you need. Okay, we're going to send it to you 1 row at a time. So you're going to have to buffer up 2 and a bit rows before you have enough data to produce 1 output. Does that make sense? And you won't be able to compute the last output pixel until we've sent you, this last value, or you put it in yourself, this last padding. And then you can compute this last one. Does that make sense? Okay, so you'll have a little bit of a startup time where you need to get all this data before you can produce anything. And then you can produce an additional output every single cycle because you get an additional input, and that's enough to compute 1 more output. Okay, so we're going to send in 8-bit data. So usually image data is not really high precision, so we're going to use 8-bit data. We're going to send you 1 pixel per cycle, and it's the same streaming interface that you used for assignment 1. There's a valid bit. So we can say, okay, we don't have any data for you right now. Okay, it's just some handshaking. You're going to write some hardware that buffers up this input data, computes the convolutions, and outputs them in row major order. Row major just means you go across all the columns of row 1, then you go across all the columns of row 2, and so on. The output format is, again, very similar to lab 1. 8-bit outputs, and you're going to tag them with an output valid signal. So there might be times where you're just waiting for more input data. You can't compute anything, so you're going to say, my output isn't valid. Yeah?
I'm assuming there's also going to be like stall signals.
Yeah, there also are, I didn't mark it on here, but there's also a ready signal from the downstream hardware that you should handle, just like you did in lab 2. Okay? Yes, in fact, I came in with the animation. So there's a ready signal coming in, and you're going to send a ready signal back. Your logic for those aren't wildly different. Okay, there's also filter coefficients. We're just giving those to you essentially as constants, okay? So you could store those on chip in registers. We're not really making you worry about that. We're giving them to you in your Verilog. They'll naturally get mapped to either constants or registers, and you don't really need to do much more about them. We also give you, to make this less confusing, we give you, you know, kind of a basic sample implementation, right, to get you going, so you don't have to worry, get bogged down too much in some of the details of how do we get this going. You have test benches and a basic implementation to get you going. You can focus mostly on optimization. So it's going to take you a little while to code that. Do it a bit at a time, right? Get a basic thing working, and then optimize. In this case, you can code everything in basic Verilog again. But when you write things in just basic Verilog, you're relying on Quartus inferring what does each one of these things mean. That works well for gates, for muxes, for registers, basic RAMs, multipliers. You know, you write times, you write some lookups, and those will get mapped to basic RAMs and multipliers. But as you get into more complicated features of specialized blocks on the chip, usually Quartus won't automatically infer those. So it'll still make your design work. It just may not use the hard blocks to their full potential. Maybe you could do multiply accumulate, for example, in the DSP block, and if you just write times and add, Quartus will figure out the times can go in the DSP block, but leave the adder in soft logic. That's not the end of the world. It's okay. But if you want more performance, you may want to just control exactly how those hard blocks are used. So to do that, basically you go to this menu in Quartus, Tools, IP Catalog. You'll see something like this. You'll see all these drop downs of different IP you can put in your design. And the ones that are interesting to you are this one. Okay, so this is called the native fixed point DSP for this chip, Intel Aria 10. By instantiating that IP, you're basically instantiating a DSP block, and it'll show you all the parameters. You can turn on pipelining inside of it. You can control what its input data width is. You can control anything you want about it, okay? So again, you don't have to use that. You can just let Quartus figure it out from your RTL, but if you want to optimize further, you can instantiate this DSP block and have full control. The other thing that you're probably going to need is you're buffering up some data. Like I showed you, you can't compute a single output value until you've got 2 full rows in a bit. And in a steady state, you need to be looking at 2 full rows and a partial row. Like you need to have this full window available in order to compute things. So you're going to want some memory to keep around what's called a line buffer. You know, keep around some of the recent data that you've been sent so that you can use it in your convolution. You can write that again in Verilog and let Quartus map it to registers or RAM, but you may find you don't like the way it maps it and you want more control. So there are two IP cores that might be useful there. One of them is this, they're all under on-chip memory. So there's a 2-port RAM. Okay, so a 2-port RAM means I've got 2 access ports. I can be reading from it at one address and writing to it at another one. That's pretty useful for what we're doing here, where data is streaming in, and at the same time, we want to be looking at some of the data in order to compute outputs. The other thing that might be useful is a FIFO. Okay, so a FIFO is actually built out of a 2-port RAM, as we talked about a couple of lectures ago. But if you decide that a FIFO does exactly what you want, you could just instantiate it instead of a RAM, and maybe you'll have a little bit less logic to handle. On the other hand, if you decide a FIFO doesn't do exactly what you want, you really want to control the RAM, then instantiating this 2-port RAM would be better. Okay? Once you instantiate it, basically a GUI pops up and says, tell me about the RAM you want, right? How wide is the data, etc. Does that make sense? And again, you don't have to do this. You can write it all in Verilog and just let Quartus figure it out, but it may not put it in RAM exactly the way you want if you're trying to optimize your design. So you can have more control by using these IP cores. Does that make sense? Yeah.
I'm sure we can figure this out by just doing it, but do we see in Verilog a module that says RAM with the exact? I hear this, or
Yeah.
like a block diagram like it does in the bottom?
So what happens when you bring this up, and it's in the handout, it'll show you actually some of how to do this, but basically you click on one of these things and say, I want it, and a GUI pops up and says, well, tell me, you want a 2-port RAM. Tell me more about your 2-port RAM, right? How wide are your data words and so on? Do you want 1 clock or 2 clocks, et cetera? And that's all graphical. It just asks you all these questions. Once you're done, it basically makes an HDL file for you with a top-level name, and you can just go instantiate that block in your HDL. So it just says, here's the module name that I just made you. Yeah, you go instantiate it once, instantiate it 50 times, whatever you want. Hook up any signals you want. You do whatever you like. Does that make sense? Okay. And that's a standard way to kind of incorporate, or a standard way to incorporate IP cores in your design. Okay, so let me remind you about, this is used for image processing, right? If you want to do any filtering or image manipulation, you tend to use these convolution operations. It's also a building block of machine learning. I imagine most people have heard of this. Who here has heard of a convolutional neural network? This is like a test to see if you put your hand up. I'm pretty sure you've all heard of a convolutional neural network. I'm testing you. Okay, so convolutional neural network, as you can guess, has convolution in it. And it basically is a little bit more complicated than what you're doing in this lab, because you're basically making a 2-dimensional convolution. And just like lab 1, you're saying, well, how fast can I make this? If I was to fill the device up and run it as fast as I can, how much 2D convolution could I do? Why is that interesting to do? Because if you do things like deep learning, there's a lot of convolution going on. This is a picture, well, that I stole from a website, and it basically just shows how does a CNN work. So an input image comes in this case, red, green, blue, so you got 3 sets of data, and you apply convolutions to that produce feature maps. So that's what this next block is. And so what are those convolutions? Well, the most classic CNN convolution, it's actually it's a bunch of 2D convolutions added together, which oddly they call a 3D convolution, but it's really a whole bunch of 2D convolutions added together. So that's what this is showing. We're scanning these convolution filters across our input data, red, green, blue, and we're producing a whole bunch of output data. And if we do this with a whole bunch of different filters, or convolutional coefficients, we'll produce a block of data that is called a feature map, okay? And then you take that feature map and you do the same thing again. You have a bunch more of these convolutional filters that you scan over that one, you produce a new one, and so on. You do that for some number of layers, and then usually at the very end, you have what's called fully connected layers, which are basically just a whole, I guess, sort of a degenerate form of convolution, okay? And then you get out, in the end, a categorization. In our final output value for a typical CNN, every one of these outputs would represent the probability of it being some classification, like a car, a truck, or a van, et cetera. Okay? There are other types of convolutions used in CNNs nowadays. So what I just showed you is called a 3D convolution, even though it's really the addition of a bunch of 2D convolutions. You also have true 2D convolutions that are called depthwise, and you have 1D convolutions. Well, another kind, a small convolution is called pointwise. So, but basically lots and lots of convolutions. So people want convolutions to go fast. That's what you're doing in this assignment. Okay, so I haven't released the assignment yet. It's probably not as scary as it sounds, right? So, I mean, how hard do you think it is? So, okay, that's not a confidence booster. Like I said, there's a contest to see who does the best, but don't kill yourself, right? Like, we don't do binary grading, so make it work. That's the most important thing. And try to optimize it to get good performance until you get bored. And then you're doing some comparisons and writing a report. And as long as you make it work and get reasonable performance, you're going to do fine. If you want a challenge, you can kind of keep going, saying, okay, how fast can I make this? Yeah?
I've already done this for another course and optimized it. Can I reuse that implementation and cite it?
Is this for your capstone or for something else?
Capstone,
Yeah, that's fine, because that's your own code. So,
I did it last week.
Yeah, if you have that for your own, you have your own implementation of a CNN, it's already fast. You have to match our data input and so on, right? So you're going to have some hooking it up. Go ahead. We're not going to make you go rewrite all the code. So, okay. So for next week, I don't expect you to read all 3 of these papers, but lots of people like deep learning these days. So here are 3 papers that you can choose to read on deep learning and FPGAs. I could give you slightly more time. How many people would like a week and a half to read these? It doesn't really matter because, again, you can pick some number of papers to read from everything. You only need to do 10 over the course. But if you're particularly interested in these ones, I can give you a bit longer so you can pick more of them. So how many people would like 10 days for this instead of a week? Or you're just like, I don't care. Okay, so quite a few. Okay, so I'll make the due date a little bit later for this one. We're going to talk we're going to take some results from each one of these 3 papers. You can find a lot more. These are all papers that I like on deep learning acceleration on FPGAs. They're by no means exhaustive. You'll find a lot of different papers on this if you go search. So if you like this, you could make this the topic of your research summary paper at the end of the course. Okay, so and then I had 3 options for this week. Well, 2 and a bonus. So let's go through the papers that were assigned this week. They're kind of interleaved through the lecture. Okay, so let me just orient you of where we are. So today what we're talking about is, I guess, 2 things. We're moving up to the system level, and one interesting application that highlights a few things in terms of compute models and strengths and weaknesses of FPGAs. So we're going to talk about how FPGAs are used in data centers. Historically, FPGAs were used more in essentially the embedded market, right? So cars, washing machines, the high-end embedded market like cell phone base stations, core routers for wired internet. But another major market for FPGAs now is inside data centers. And that wasn't their traditional market, so it's been interesting to talk about, like, how do they fit in there? What are some of the interesting papers? So we're going to talk about that, and then talk some about how they, well, strengths and weaknesses and use cases in deep learning. And again, you can go a lot deeper on that if you want than I can in one lecture. Okay, but the very first thing we're going to do is kind of finishing off what we were talking about last week, like how to do good comparisons. So this is a paper that is, well, it's a bit older now, but I think it's a classic paper by Intel, taking a bunch of published results on GPUs, saying these algorithms all run really, really fast on a GPU, and redoing the analysis themselves to compare a GPU versus a CPU. How many people read this paper? Okay, what'd you think? Did you like it or not? How many people liked it? Okay, Alex liked it. You liked it. Okay, that's good. So I mean, if everybody hates a paper, I'll just take it out next year, so don't worry. Even if it's my own paper, don't worry about it. Right? Like, I'll put a different paper in. Okay, but it seems like people like this. Let's see. So before I go to the next slide, what did you like about it? Anybody want to summarize what you learned from this paper? Because I'm hoping that you liked it not just because it was short, but because it had taught you something. So what do you think? So is it, or what do you think?
Yeah, one thought that came to mind, more just like in the critique section, I guess I'm gonna say is, just because people don't always write optimized code for CPUs. I'd say most code in industry is probably not micro-optimized, certainly not to the level that they were doing it there. So I'd be interested to see on like more typical, what can an average GPU programmer and an average CPU programmer do?
Yeah. So I think it's a good point. I mean, the key takeaway from this paper was, I think, it's not fair to do a comparison where you didn't optimize a lot for both platforms or equally. Now, that's a difficult thing to say you optimized equally, but I think Intel did a good job in this paper of showing a lot of GPU papers that had been published to that date had not put much effort into optimizing for the CPU. So it was kind of an unfair comparison. Yeah?
Another thing I noticed was that they did the comparison. They said, oh, it's not actually 100x or 1000x. It's actually closer to 5 or 10x. But they didn't have any conversation about how GPUs could improve, because hypothetically GPUs should be better for throughput than CPUs.
Yeah.
I expect that number to be much higher.
So it's interesting. So you thought, why is it only 5x or 10x? Okay, so let's come back to that. So this is the key. I'm going to go through this paper pretty quickly. The key thing that they come up with is that a lot of these papers claimed 100x performance improvement. And when Intel went through and did their own study of this. They found the GPU generally was faster. They didn't say GPUs were slower, although these are speed up numbers. So you can see there actually are 2 applications where the GPU was slower. Speed up is less than 1. But usually it was faster, and on average it was 2.5 times faster, which is actually not bad, right? So you're 2.5 times faster, that's pretty good. But it's not 100. And it did vary, right? So this one was 14.9 times faster on the GPU, which is a lot. What are these applications? They seem like pretty reasonable applications. So this is single precision matrix multiply. So it's a building block of a lot of things, including some deep learning applications and a lot of matrix math that you use in scientific software. A Monte Carlo program, which basically means you simulate random events to try to build up a picture of what's going on. Convolution, right? So I told you convolution is important. FFT, which is basically if convolution in the time domain is starting to get too painful, transform it to the frequency domain and do multiplication. So signal processing is important. Saxby is another linear algebra operation, and so on. Some searching, some sorting, etc. So I'm not going to go through all of them, but they're pretty reasonable applications, in my opinion, like that are many of them very important. Okay, so why did they not? Well, we already heard some of why they got a different answer. I guess the number one reason was that the CPU code was not as optimized as it could have been. And why am I telling you this in a course about FPGAs? Because you see the same thing in FPGA comparisons. Somebody will spend a year or 2 years optimizing an FPGA implementation, and then they'll download some code from GitHub, they'll compile it, and they'll say, and that's what I got on the CPU. And it's like the laptop I had, because that was what was handy, right? So you don't want to do that. It's difficult to actually say you put equal effort into 2 things, and sometimes you don't have to. Like you just run out, you hit diminishing returns at a certain point, you know there's not much left. But you want to try harder than that. And it is a common problem. It's not just CPU versus GPU comparisons. Yeah?
For a lot of tasks, though, I mean, convolution comes to mind. I think the machine learning libraries that you would just download off the internet and run are going to be well optimized for CPUs as well as.
Yeah, and that's a good point. So so this is a deep question. Sometimes you go, well, wait a sec, so I should apply equal effort. That's probably a reasonable way to do this. What if there are really good libraries on one versus the other? Well, then it's fair to say I could get really good performance on this platform quickly because there are great libraries. On this other one, I couldn't, and I capped the optimization effort at this much. I would say that's still a fair comparison. You're just saying this is not a comparison where you're willing to go rewrite a library. So if it doesn't exist, or maybe the programming model is so much harder on one device that you did spend a bunch of time trying to optimize it, but you just didn't make much progress. I'd say that's also fair. Does that make sense? What you do want to avoid, though, is, this was hard. I did hand code a ton of CUDA. It took me a really long time, and I was really tired. And then I pushed the button on my compiler on the CPU and ran on the machine closest to me. And then you get the question, well, is this reasonable? Intel has a vested interest that perhaps, well, maybe not even perhaps, they would probably like the CPU to look good because they sell a lot of CPUs and not so many GPUs. So, but my personal belief is they did a pretty honest job here, right? So what did they find? Well, basically, the number one thing is SIMD. That was the biggest single thing. And at the time they wrote this, the compilers for CPUs were pretty bad about using SIMD, but Intel processors, like most, did actually have SIMD. They had, for floating point, which most of these applications use, they could do 4 floating point multiply accumulates in parallel if they use SIMD, and they could do 1 per instruction if you didn't. So it's a 4x difference. And the GPU also has SIMD, but its programming model sort of fundamentally makes you use that SIMD. They call it SIMT, but it's effectively the same thing. So that was the biggest thing, is that they used the SIMD units on the CPU. Do you think there's any? Okay, so it makes sense from a hardware perspective. The CPU has SIMD units. You should try to use them. Is there any argument that the GPU makes it easier to use the SIMD units? What do you think?
So when the compilers are trying to automatically create SIMD, it's hard for them to recognize SIMD patterns, as you say, because it's hard to recognize the loops are in the right way to actually access data in that way. So you'd have to use the AVX 512 or whatever it is interface, which is much less portable. So if I have an Intel Core i7 and I
Yeah. Yeah, so I think it's a good point. So on the one hand, Intel's right. It's unfair to the GPU to not use the SIMD instructions. This across the top is basically peak performance. They're taking a GPU and a CPU that were the same process generation, roughly the same die size. So they're comparable, because that's something you want to do too. Well, here are the transistor numbers. The GPU actually has more transistors. So one thing they flagged was literally some people just ran on their laptop versus a high-end GPU. Okay, so they said don't do that. So they chose two comparable chips. And if you look at them, they've got 4 cores in the CPU, 30 of these streaming multiprocessors or core equivalents in the GPU. CPU runs faster by about 3x. The GPU has more memory bandwidth by about 4x. The GPU has a higher SIMD width, but because the CPU can do 4-way SIMD, the GPU can do 8-way. That flips at double precision. GPUs usually don't put much effort on double precision. So they're big functional units. They don't bother building that many. So basically, if they don't use the SIMD units, they get one comparison in terms of how many floating point operations they can get. If they do use the SIMD, they get a different peak number, and that's the one that's more relevant. So they found that basically the GPU has about 6 times the peak floating point operations and about 4.7 times the memory bandwidth, which is closer to the 2.5x they get in the end than the 100x people claimed. But they had to hand code the SIMD instructions. The compilers weren't very good about doing it, and that means writing almost inline assembly. They're called compiler intrinsics, but it's like in your C or C++ code, you're almost putting in something like the splits assembly. I would say it is actually harder to do that than to write CUDA code. So Intel arguably put more effort into optimizing this than the GPU developers did, and it is less portable. It is annoying with these SIMD instructions that every time Intel or AMD widen the SIMD width, so they go from 4-way to 8-way to 16 width, they basically change the instruction. And if you've been manually writing those assembly-like instructions, you have to go in and change your code. And something that NVIDIA did that's very smart is CUDA kind of hides that. You have to be thinking about the fact that this has to be highly parallel threaded code, but you don't have to be thinking about, what's my SIMD width and how many cores do I have? You just don't think at that level of detail. So yes, they probably went from a spot where the people were under-optimizing the CPU to arguably they've probably spent more effort now on optimizing it. So that's the biggest single thing, though, is using SIMD. You're going to, in assignment 2, you're going to play with the compiler a little bit on the CPU code we gave you. And compilers are getting better at using SIMD automatically for CPUs. So they used to be very badly on it. I would say now they're doing somewhat better. But still not as well as you do with CUDA and a GPU compiler. That was the biggest single thing. The next thing they had, though, is that on a CPU, the way you optimize is a little different for the memory subsystem. So a lot of these are using big data sets. So they're doing matrix operations on big pieces of data. And if you code that in the simplest way, like say you code matrix multiplication as just 3 loops walking through your big matrix, it doesn't work very well because you spend all your time waiting for memory. But you can recode that with essentially more loops where you keep going over little bits of the matrix and computing sub-results that you'll later add up. So that's called blocking, right? Try to do all your compute on a portion of your problem, save those results, move on to the next one. It works much better with caches. A GPU, because of its model where it just has lots of threads, can say, no, just leave it in main memory, and it's so long before we need this data back. We have so many other threads to switch to that it's okay. The CPU doesn't like that, so you write it in a more complicated way. Some of the time, people didn't use more than one core. They just wrote single-threaded CPU code, and that's very unfair, right? Because if you write single-threaded GPU code, your performance is terrible, right? So nobody does that. So you should multi-thread your code. And in some cases, like a CPU does spend a lot of effort on making branching very efficient. And sometimes you can use a more clever algorithm because of that. It's not as brute force, but it has more if statements. And where that was possible, they did it. Let's see. And basically, the GPU had the opposite, right? So when everything's very regular, it's going to do extremely well. Has more trouble with branching code, which tends to show up when you have a clever algorithm. Anyway, because I kind of already told you this, there's like a morality tale on FPGA results. So I remember one of my master's students some years ago. I told you told you about him before, you may not remember. He did a big SIMD unit on an FPGA for LU decomposition, matrix factorization. He compared it to just taking a well-written code from a well-known numerical textbook, typing it in and compiling it, and he was 20 times faster. And then we went and got Intel's math kernel library, which is their hand-optimized code. And that code was, I think, 16 times faster than that baseline implementation. So it was like, it was the right thing to do, but it's like, whoa, they did a good job writing this. They used SIMD, they used multiple cores, and then they actually just did a bunch of clever stuff that actually got even more than we thought. So you do want to go compare against the best. So they used 14 benchmarks in the study. 3 of them were memory bandwidth bound, and of those 3, 2 of them, their performance was actually close to the memory bandwidth ratio of the CPU and the GPU. The other one was harder to predict because the CPU's cache could help it. So it did better on the CPU than you would think just from memory bandwidth. 5 of them were compute bound, so they could fit, it was really about computation, not about getting data on chip. And their performance was predictable by just looking at what data type they used, single precision or double precision, and looking at the peak performance ratios. And then the last 7 of the 14 that were harder to predict, right? So their structure was more complicated. You couldn't predict as much. Okay, so why did I tell you this? Because, I went through a paper last week that was about finding peak performance numbers, right? Peak compute density, peak memory bandwidth. So in this particular case study on a CPU versus a GPU, those peak metrics actually let them predict correctly what would happen in half the cases. So peak isn't meaningless if you choose the right peak, but it's not the whole answer either for many applications. Okay, that's all I had on that paper. Any other thoughts or move on? Okay, so I'm going to move on. So it's basically a study and benchmark carefully. Okay, so the next 2 papers that you could choose to read. Well, how many people read one of these papers? A couple, 3, 4 people. I like these papers. How many people read both? I'm wondering next year if I should just remove the potential bonus one, as just nobody's going to do that. Okay, at least one person. Okay, so that's good. What do you think? Those who read them, did you like them or not? Yeah.
I didn't like the second one because the first one, I read the first one first and the optional one second, and it turns out the optional one came first. So I ended up like, oh, I already know this because I read this in the last paper.
Oh, okay, so wait a second. You read this one first, the 2016?
I read the one that wasn't optional first. I read it in order on the screen.
Right.
And then I also didn't like the first one, the non-optional one, just because it was so hard to follow. They didn't do a really good job of explaining the outline.
Just making sure I got like my optional and not optional one. So did you like the 2016 one and not the 2014, or the vice versa?
The 2014 one was more organized.
Yeah.
The 2016 one was more relevant.
Yeah, okay. So I think that's true. I actually really like I like both these papers, but the 2014 one, which is less relevant because the 2016 paper says here are the various mistakes we made and that we've now fixed. So if you read one of these papers, probably reading the one where they say don't do it that way is probably the right one to read. But the 2014 one is a very well written, very clearly organized paper that I liked. Not that the 2016 one isn't. It's just the 2014 one, in my opinion, is just extremely good in terms of its clarity. So.
And also in the questions you gave for the 2016 one, you gave it a name, which they never called it in the entire paper except for the conclusion.
Huh. Which is, okay,
They called it something too.
Catapult 2.
They didn't call it Catapult 2. They didn't mention the paper except for in the conclusion.
Oh, I'm glad it's in the conclusions to make sure that I didn't just make that up. I'm just asking you impossible questions. I just. Huh, interesting. Okay, so I'm just going to kind of talk about these 2 together because they are both coming from a really big project at Microsoft. So, okay, so Microsoft was the first data center operator to deploy FPGAs in their data center in a big way. Okay, and this was a big thing for the industry. I actually know, like Altera won this design win, which ultimately turned into an FPGA in every single server that Microsoft has, which is a lot. And it's actually, if after class you can ask me the story of that. It's pretty interesting. The people at Xilinx who kind of messed it up got in a lot of trouble, right? So they didn't pay attention to what could have been a giant customer. So it was a big mistake. But it started with this project of So Bing, right, Microsoft's competitor to Google, is a complicated algorithm. It's deployed across thousands of servers, and they want to reduce the cost of those computers, so don't need so many computers, reduce their power, but they don't want to increase search latency. So latency is a really big deal in all these services. They combine all sorts of results to get the final answer, and if it doesn't come back quickly, they just alienated the end user and they go away, right? So you got to get a good answer quickly. They want it to be scalable and reliable, so what they call data center class. And it's interesting. So when Microsoft talks about this, academics often go like, our results scales to like 2 or 4 or maybe even 8 FPGAs, and they're like, we don't care until we don't start at numbers less than 1,000, right? Like that's where we start talking about scaling. Why FPGAs? So the reason they looked at FPGAs in 2014 and again 2016 is basically Moore's law slowing down. So it's like the age of the accelerator. For many, many decades, if your code didn't run fast enough, well, you try to optimize it, but you could also count on in 2 years, approximately, you get a faster processor, or you get more processors for the same amount of money. And that's getting weaker. Okay, faster, definitely not getting much of that anymore. You still are getting more processors per dollar and per watt, but it's slowed down. So this meant that, and it also is taking longer for the next process generation to come up. So it's making building customized hardware more compelling. You have less risk of being late because it's going to take longer for the next generation to come out, and you're not as excited about the next CPU generation. But at the same time, the demands on data centers just keep going up for reasons that the data center operators like. People want to use more and more processing. They want searches. They want AI. They want to stream videos. But they want to make their data centers more efficient because of that. So they're willing to now look at essentially more complicated solutions with accelerators. So some of these slides I've stolen from Andrew Putnam, who's a senior engineer at Microsoft, who was part of this project. And it's just kind of interesting. What does a data center look like? So a data center is hundreds of thousands of servers. They mostly don't have people in them. Individual servers fail all the time. They mostly don't bother repairing them. They just leave them alone and route around them. So they have to have reliability that they can basically send jobs to different machines because this machine's dead. It can't have any effect except they're some tiny fraction less efficient. They're hostile environments. He said, like, going in and fixing things is hard because at least the time he did this, he said the data center is so hot they would send people in if they had to do something in like fireman suits, right? Like sort of protect them from the heat. So they're like human hostile environments. They build them, they run them. They usually don't fix the machines. If they die, they just, after 4 years when the machines are all going to get pulled out, they'll pull it out. And basically the machines are unreliable. It's not a goal, but when you have this many machines, some will be broken. But the data center itself has to be unbelievably reliable, right? You never want to be the person, reading the newspaper and going, I'm going to have to, I guess the CEO is going to be phoning me shortly to say why the data center's down, right? Because you would get that call. So Microsoft, like most data center providers, makes their own servers. So they spend a bunch of time optimizing the servers, and they value homogeneity. They'd really like to have a data center where they have one kind of thing so that if things break, they can just route around it. If they have to scale up an application, they can just give it more. But they don't have like 10 kinds of different accelerators or different servers. Like they would prefer not to have that. They do have some of that. They can't avoid it sometimes, but they'd really like to minimize that. So CPUs are great for that, but they're not getting as much performance out of them as they'd like. So what they did for Catapult, the first generation, is they basically already had their server architecture. So they could squeeze in a single FPGA, give it 25 watts of power by putting it in a PCIe slot. They actually couldn't fit or power a GPU. Their main quality metric was performance per watt per dollar. Okay, and this is just like essentially an approximation of the total throughput per dollar. They spend, the numbers vary, but usually here they're about 30% of the cost of a data center over its lifetime is power, with the remaining being, you got to buy the space, you got to buy the computers, and so on. So basically the cost of the chips matters, but the cost of power also matters. They just blended it together in this one metric. Let's see. Yeah, at this time, the machines would last 3 years before they were kind of obsolete. They'd turn them off. That's now stretched out to more like 4 years. It's again a sign that Moore's law is slowing down. And about halfway through their life, they go from being like the premier servers that a major, sort of the high-end services like Bing would use. So Bing tends to get the best servers. Halfway through their life, they're still useful, but they're kind of moved to sort of lower priority tasks. And I guess I already mentioned this. They really would prefer not to have all sorts of different kinds of servers and accelerators. They'd like it to be homogeneous if they possibly can. Okay. But at the same time, you know, to get more performance than for a long time, this meant use CPUs, right? That's homogeneous. You can do anything on them. But they now want to do better than that. They want to specialize to their computation some, but they'd still like their data center to be homogeneous. So that's where they basically said, okay, FPGAs would be a good fit to that. And they don't go for the highest end FPGAs because they don't want to pay the highest premiums. They don't want the highest power. They go for sort of the mid-range. And they don't want to say, I can offload from this one CPU or these 2 CPUs in this server to this one FPGA. It's a data center. They want to be able to say, I have a huge number of FPGAs, a huge number of CPUs, and ideally I can split my computation in all sorts of different ways. Okay, so this is their first generation Catapult. And it's a small FPGA card, a mid-range part of that time. Let's see. It was important that they wanted to keep their CPUs. So because they kept the power down to 25 watts, they could keep both CPUs. And they put in this custom wiring harness. So basically, the data center has networking between all of these machines. The networking connects to the CPU. And then the FPGA over PCIe, well, one of the 2 CPUs can. And then they put in a special wiring harness to let the FPGAs in a rack. Okay, a data center is built out of all sorts of racks, and then you connect all sorts of racks together with switches. So they put a special wiring harness that implemented a torus that is basically 6 by 8 servers with their own custom serial links, because they know this will be reliable and they want it to be low latency, so they made their own serial protocol, and they used the custom I/O of the FPGA to implement that, and that's what they got. They get 48 FPGAs in half of a rack, okay, one in each of the 48 servers. They can talk to the CPUs. Through the CPUs, they can talk to the network, and through this special wiring harness, they can talk to each other. But they can talk to each other in groups of 48. Does that make sense? They wanted to make it easier to program the FPGAs and for developers to use them, which is a big issue. Okay, so they got tons and tons of software developers. These software developers don't know what an FPGA is or how to write HDL. So they're not trying to teach all the software developers to do that, but they are trying to make their hardware developers as productive as possible. So they designed what they call a shell, and this has now become standard. Other people have adopted the same style. So basically, they took everything that talks to the outside world. So the DDR interface, the network interface, PCIe, and they basically said, that's the shell. You don't touch that, right? So you as an application developer, you're just going to talk to that logic. They pre-place and route it. So they run Quartus with just the shell. They let it choose where to put all of the logic, et cetera. So some of this stuff would be hard logic, a lot of it's soft logic. So they actually wind up using 23% of the device just to implement this shell. And they lock it all down. So in Quartus, you can basically say, take that part of my design that's done and just lock down its placement and routing, never touch it again. So they did that. And this means you can just kind of forget about it. Okay? On the one hand, maybe in your particular application, you didn't actually need, I don't know, say DDR. So maybe it's a bit of wasted logic. On the other hand, you didn't have to worry about any of this, right? Like all of that talk to the board peripherals and the rest of the network and stuff was done for you. The logic is correct. It's locked down. It for sure runs at a fast enough speed. So they considered that a good trade-off. Does that make sense? Yeah.
I had a quick question while reading the paper. I noticed that there was a part of it where they didn't use 100% of the FPGA. So they had an area for the there was like 20% of the device still unused. Is there a reason why they left that 20% or so?
I'd have to go back and look at it. I mean, it may be that they just didn't know how to like make use of it given their application,
That's what I was wondering.
like that they just ran out of design logic. Another thing is that sometimes when you go to 100% utilization of an FPGA, it gets hard to route. And so your compile times go up, or you might fail, or your frequency might go down because the CAD tools are a little bit desperate just to fit everything. So often people don't want to go all the way to 100%.
I see.
Except Huawei. When I was at Altera, Huawei would go to like 99.99%. And if you didn't route at that point, then you would get a phone call. So it's just, I'm actually not kidding. So, and they were a big enough customer that you had to take that phone call and say, I will, that's fine, right? Yeah, we'll make that 0.01% work. So it's cost efficient, but most people leave a little more margin than that because they don't want to worry about it. So the first thing that Microsoft did with this was they wanted to optimize their Bing search algorithm. And they've never revealed exactly what the search algorithm is, and it's changing all the time. So this was not like a static algorithm. There's some information about it in the paper, but basically from your documents and your query, they extract all sorts of feature indicators and things they call free-form expressions. They apply some machine learning algorithms, et cetera. So they do a whole bunch of scoring of which of these features occur in the document that were in your query, how close are they, et cetera. And they never say exactly how it all works. But what they do say is basically it doesn't fit. The algorithm doesn't fit in one FPGA. So they basically split it across 7 FPGAs. They didn't need all 48. So a torus basically is just a 2D mesh with wraparound connections. So it has rings inside of it, right? It has more than a ring, but they basically just used it as a ring. They used it as basically 6 independent rings. Each of them have 8 chips, talking in kind of a serial fashion. And their algorithm is like a feed-forward algorithm. You know, your result from one thing goes to the next. So they split it across 7 FPGAs. And then one of those 48 FPGA half racks, they could do that 6 times. They split it across 7, I guess partly because they only needed 7, but also because they wanted to leave a spare FPGA. So by leaving a spare FPGA, it means if one of these servers FPGAs is broken or something wrong with the server, as long as it can at least pass through data, they can basically just reprogram the other ones to essentially have some fault tolerance. They only need 7 out of these 8 FPGAs to work, as long as you can at least pass data through. If you can't pass data through, then it is broken. But that's a pretty, I guess, a less likely failure mode. It's also interesting because this system is very dynamic. So the Bing search engine, their software developers are constantly updating it. But not every piece. You know, some of the more low-level processing doesn't change quite as fast. But they were worried about mapping this straight to hardware with no programmability. So they built a form of overlay. They basically made a hand-designed data path, okay, so written in Verilog by people who know how to make hardware. And then the control of that data path was a finite state machine. So this is like the finite state machine plus data path compute style. And that finite state machine was automatically created from basically a domain-specific language they made, like something that their software developers or search engine architects could use, and it would automatically make the FSM. And it controls a data path that was designed for efficiency by hardware developers who were pretty good at what they did. So interesting, right? So they used one of the programming models we talked about. Okay, so what did they get? This is the first version of Catapult. They got a 95% improvement in throughput at the same latency, so almost twice as much. The next paper they had, Catapult V2, increased that to 125% throughput improvement, basically by moving more of the algorithm to hardware. And software was still the limit. So they said that this is basically getting, 2x, maybe a bit more than 2x throughput improvement. And what's limiting is not the speed of the hardware, it's just there's a lot of the algorithm still running in software. And that's actually the bottleneck. So they need to move more of it to hardware. The power increase, because this was kind of their key metric, was throughput per watt per dollar, less than 10%. So they're very happy with this result. And because of it, Microsoft actually deployed Catapult across the the Bing part of their cloud, which is, Andrew would never tell me how many servers that was, but it was clear it was at least tens of thousands, right? Just by asking lots of questions, buy him another beer, and binary search this, and it was definitely at least tens of thousands of servers that they deployed this on. So it was a pretty big deployment. He also said it was very interesting. They submitted, the Catapult paper, which is a great paper, and some of the reviews came back and said, basically, you only got 2x performance improvement. Man, can't you get 100x like those GPU papers or some other FPGA papers? And he said that this is in his opinion, the difference between industry and academia, that in a Microsoft production environment like this, like 2x is a really big deal, right? Because the system is very optimized and there's a lot of money that's been on the line for a long time. So people don't get like 100x, right? So I think those reviews really annoyed him. But despite that, the paper got in and it's a great paper. So, okay, but that's not the end of their story. So, because they then did the second paper, which is Catapult 2. So what is Catapult? Well, maybe I should pause there. So any questions on that? Seems to make sense. Maybe you've gone to your happy place. I guess we'll see you at the break. Okay, so they went on to Catapult 2. And what is Catapult 2? They basically re-architected how the FPGAs and CPUs talk to each other. So this is what the Catapult 2 hardware looks like. So they have two CPUs again in their server. And these CPUs are not cores. These are like, sockets with multiple cores in them. So they're big, beefy Xeons. The data center has basically racks. Every one of these things that I'm showing here, these little boxes, would be like a rack of servers. So like 96 servers, each with 2 CPUs in a rack. And they've got lots of those. There's a top of, well, actually, I guess it's like this little area here would be those servers, actually. So it's not one box. It's like one rack. Okay, so they've got a top of rack switch where all your Ethernet cables come in, and they can all talk to each other. And then if you want to talk to something that's in a different rack, you go to a higher level switch, which gets you to some local area in the data center, say an entire row. And if you want to go farther, you go to a second level switch that actually can talk to different rows, and now you can get to anybody. So through one switch, you can get to your own servers in the same rack as you. 2, you can get to, say, your row, and 3, you can get to the whole data center, which is a very large number of CPUs and servers. And basically what they want to do is consider the hardware to be disaggregated, that they have just a plane of CPUs, that's what I'm showing here, and a plane of FPGAs. And ideally, they'd be able to map applications that need lots of CPUs onto this plane, and at the same time map other applications that need lots of FPGAs onto the top plane, and map applications that need some of each onto both, that have more flexibility than they had in Catapult 1. And let's see, and they wanted to do all sorts of different things with it. So one is offload the CPU, which is what they did with Bing. But they also wanted to do just have the FPGAs be able to communicate with each other to accelerate some application. And later in this lecture, we'll talk about Brainwave, one of the papers that you can read next week, where they did that for machine learning. And then probably the most compelling thing, the one that they made the most use of, is this, bump in the wire. So bump in the wire means the FPGA can process the data on its way to and from the CPU. Why can it do that? Well, basically, they put the FPGA right in the network path. So this is the top of rack switch. This is the FPGA. So Ethernet comes in, right, and goes into the FPGA. That FPGA can then send it onto the CPU. It can also send it on to a simple network interface to the other CPU. Okay, so this has actually kind of flipped the way it worked in Catapult 1. Catapult 1, the CPUs could talk to the network and to each other, and they could ask the FPGA to help them with something. Catapult 2, the FPGA talks to the network, and they can talk to each other. And if they think they need the CPU to do something, they send the data onto the CPU. So they've kind of flipped who's attached to the network and who's in charge. Does that make sense? Okay, and so that's one big change. The other big change they did is this torus is gone. Okay, they basically, by connecting the FPGAs to the network, They just say the FPGAs communicate with each other through the network, and if the CPUs want to talk to each other, they talk to the FPGA first, right? That's how they get to the network too. Okay, so they got rid of this, yeah.
Quick question, when they would do something like this in the data center, would they redo, remove the Tauruses, or would they just do this for their newer servers?
They do it for their new ones. Like basically you move on to, you're kind of never going to go back and update. That's the kind of their whole philosophy. Like even if things break, they usually are not fixing what broke. They're just kind of like, it's in the cycle that in 4 years this hardware is going to be renewed. At that point, it's all being thrown away.
And wouldn't that basically mean that nobody could write applications for the older one? Because why would you target something that's going to be removed within a few years?
Well, that's a good question. So let me answer that by showing you this. So the first thing they did is this is an interesting plot. Okay, so it's basically how many FPGAs can I reach, or CPUs as well, because I could go through the FPGA to the CPU, and what's my latency in microseconds. So that's pretty fast, actually. This is like 5 microseconds. These latencies are pretty small. What I'm showing here, this red line, is what they got with that 6x8 Taurus. So with the 6x8 Taurus, they could get to 48 different FPGAs, and that's it. Right? You couldn't use the Taurus anymore. You had to talk to the CPU and have it send something over the network if you needed to go further. And its latency was pretty good. But when they compared that to just going through their existing switches, they basically get this bumpy line. Okay, so if they're in the same rack, basically, they get this line. Once they go to that level 1 switch, which say is a row or a local region, they take an extra hit in latency, and if they go whole data center, they go up here. And the green here is showing there's a bit of jitter on this. Like they're not really just lines. The lines are the middle, but there's some jitter based on network contention. So what this means is that the Taurus wasn't much faster. Okay, it was a little bit lower latency than the first level switch if you're right at the FPGA next door. And at 48, it was a little worse. And after that, it couldn't do anything. So they didn't cost much in terms of latency, but they get much more scalability. They can now go whole data center. They also made it much easier for their developers. So there's a whole craftsmanship to building a data center scale application where you're also optimizing network bandwidth. How do where do you put things on various nodes? How much communication can you handle? Trying to teach those developers about this new, not only is this new hardware unit called an FPGA, it also has this new communication style called a Taurus that goes up to 48 and then stops. That was a hard sell. So just saying we just have switches like you've been using for many years was much easier. So it was a much easier learning curve for people. And basically the Taurus didn't really have much advantage, right? Does that make sense? So this would actually be kind of invisible to everybody who's above the shell, because the shell is abstracting your communication. I mean, I haven't verified this because I didn't write code to it, but it's likely that they didn't actually have to recode all that much because the shell insulated from it, and because the latency is, even in the best case, was not that much better with a Taurus, so probably it didn't crater your application. Also, they said that this Taurus wiring was a pain, right? So you've got these, a 48 node Taurus is actually a fair amount of wiring. So you had to make these special wiring harnesses and go in. They're another failure point. You don't want failure points in your data center if you can avoid it. Okay, so it still uses that shell that abstracts all the housekeeping, all the I/O, etc. And the part where you put your logic, they call it the roll. So it's like a floor planned region inside the middle of the chip, basically. Catapult 2, the shell got more powerful. And so it actually now used 44% of the FPGA, mostly because it had a more powerful network interface, and that consumed a lot of extra soft logic. So that's a bit painful. I believe that's come down since, because this actually produces a lot of pressure on FPGA architects of how can you make shells more efficient. Can you take some of that logic and put it in your I/O controllers in hardened logic so this thing gets smaller? But it actually shows, yeah, these shells can get big. So it's kind of an architecture question how to do it better. The FPGAs, because they're between the CPUs and the network, they can do all sorts of on-the-fly processing. So they can do compress and decompress on data, and FPGAs are very good at this. Compress and decompress is a natural streaming computation. So you can make better use of your data center network bandwidth by just compressing everything coming out and decompressing it coming in. And you're not loading the CPUs. You can do the same thing for encrypt and decrypt. And they use that in their secure Azure cloud. So Microsoft uses its clouds for a bunch of things. They use them for their own services like Bing, Xbox Live, and so on. And they also will sell them to other people, which is Azure. You're a company and you rent capacity. A portion of Azure is secure. What that means is the data is all encrypted. Okay, so it doesn't come off the servers unencrypted to be highly secure. And I visited Microsoft a few years ago, and they were telling me how secure that is. Like, so they have encryption keys that are, for each customer, and they have a master encryption key that's used to create the sub-encryption keys that go into the various servers. And when you want to change a master encryption key, you have multiple people from that company show up in separate cars with different parts of it and go into like locked and guarded rooms to update the key. So, because, it sounds kind of funny, right? This sounds kind of Mission Impossible-like, but then you can also imagine, well, let's say this was, I don't know, the IRS, and you basically have like some data breach where they say, yeah, we left the key in the taxi, and I guess like all of the tax records are now unencrypted, right? So yeah, it's big business to be able to keep all of that data highly encrypted. Like in the secure Azure, the security is pretty significant. Yeah, so these are the benefits. They can do this bump in the wire processing. The FPGAs can all communicate without CPU involvement. What if the FPGA goes down? So is there any downside to this arrangement? What do you think? Yeah. You lose that isolated, yeah, the CPU goes down. What if you put a mistake in your upload? Like you put a new shell in or a new compressed, decompressed that's more efficient, and you put it in, but it has a bug in it, right? You could reprogram it, but let's say it takes the whole data center down. So this is something that actually worried Andrew a lot, right? So they like the architecture, but they're now on, if they actually have a bug that takes down not one server, it takes down every server. They don't notice it for a while, and then they all go down. His description was that would be a career decision, right? So he clearly visualized the consequences of that. So what they did is, because they worried about this, they made sure there was a safe configuration that didn't do much except connect the CPUs to the network that was always available in Flash. Okay, so if they ever did a bad bitstream update, somebody wasn't careful enough, a hard reset, basically, of the FPGA would always load this in, and at least you'd reconnect. So this was successful, and they rolled it out to all their data center servers. Again, Andrew wouldn't tell me how many that is, but by a process of binary search, it's clearly more than 1 million, and growing apparently at 30% a year. At least a few years ago, that's what the number was. So it's a huge number. Like this is why I say like this was a huge design win, right? The fact that Altera got this and Xilinx didn't was a really big deal, because this is such a huge number of ongoing chips, high-end chips that you're selling. Well, they're mid-range for FPGAs, but I guess mid-range for FPGAs is still reasonably expensive, right? They're not going to buy 1 million of these chips where it's like, yeah, you make up the price, right? Like maybe charge me, I'm a big customer, charge me 2,000. I mean, that's too much. Do you know what I mean? But they're still not going to be like $10 chips. Does that make sense? Okay, so that's the biggest success story in data centers for FPGAs. Some other ones, Netezza is a company that IBM bought, and what they did is they integrated FPGAs into the I/O path of basically disk arrays. And it was to speed database searches up. They sped them up by a factor of 10 by basically doing the most data-intensive, simplest database queries right there, filtering the data and only sending back the data that passed the first level filter to the CPU to do the rest of the combine and join operations. You'll see a bunch of products from AMD, Intel, and others that are called data processing units or infrastructure processing units. That's basically, Microsoft did this first. That's what their bump in the wire processing is, like process data coming in and out. These data processing units and infrastructure processing units are basically, you can come buy them from a company that makes them, often out of FPGAs, sometimes out of ASICs, or from AMD or Intel, and plug it into your cloud infrastructure. And it'll accelerate your compress and your decompress and your encrypt and decrypt and some other functions, and you could change it if you want. So basically, all of this stuff is basically Catapult-like, but sold to other people now. Intel acquired Altera, and their stated main reason was because of the data center movement, okay? They wanted to make sure they owned everything in data centers. It's kind of the most profitable market in well, at least traditional computing. Now, Intel is now partially IPOing Altera back out, so who knows? Part of that, I mean, businesses do different things, right? Part of that is probably that Intel is now trying to raise more money for its foundry strategies. They want to invest more money in manufacturing because they decided that's the heart of the company. They're still keeping the majority stake of Altera, which is now called the PSG, or Programmable Systems Group. So what does this mean? I mean, it means FPGAs have had success in data centers, maybe not as much as Intel initially hoped, right? Where like every data center operator will be using them all over the place, but Microsoft is using them in all their nodes. Other data center providers, it's harder to say, but the fact you see these products of IPUs and DPUs built on FPGAs imply at least some of them are doing similar things. And AMD has now acquired Xilinx, okay? So they're kind of, Altera went inside Intel, now it's come back out, but Xilinx went inside AMD. It also appears data center market was a key part of this. Basically, both AMD and Intel really like the data center market and want to own things next to it. The other markets for FPGAs are not going away though either. So they're kind of split now. Data center's a big market, but the embedded, you're going in a custom box all over the place is also a big market. And I couldn't tell you which one is bigger. They're both significant. So does somebody have a question or not? Okay. Okay, so another couple things that are related to data centers. How do we connect the CPU and FPGA? So, okay, so I told you Catapult V2, the FPGA connects to the network, and that was a big change. It still has to connect to the CPU, and in the original Catapult, it connected with PCIe, and then PCIe, you have which generation, so it's Gen 3, and then how many data lanes, so how wide is it, by 8. So that provides 8.5 gigabytes per second of bandwidth. It's fairly high latency, higher latency than going to main memory. It's a standard bus. And PCIe is an I/O bus, which means that the OS has to do some extra work to communicate over PCIe from a CPU to an FPGA or another accelerator. Basically, the CPU is using virtual memory. And in order for the OS to make the data go over PCIe reliably, it has to basically do usually some extra copies, copy it from wherever it is in main memory to some pinned memory, like some memory that I guarantee will be in this physical address so that the FPGA, for example, could read from it. So this is how most communication between FPGAs and high-end CPUs happens, over PCI Express. But it does have this kind of pain of there's usually an extra copy happening behind the scenes, and it's relatively high latency, which means it's best suited to kind of bulk transfers, move a whole bunch of data and then do a bunch of processing. So there have been a couple of efforts to make alternative interfaces. Physically, they still go over PCIe. Okay, so that means it still connects physically to PCI Express. You don't wind up with new connectors, but they layer a protocol on top of that. And there are two that have been reasonably successful. One that IBM made called CAPI and one that called CXL that Intel made. The key difference with just basic PCI Express is they can use virtual addresses. Okay, so you don't need to, the OS doesn't have to copy data, kind of lock it down in certain physical addresses before transfer. Instead, when the FPGA here, or accelerator, asks for data, it goes over the PCI Express bus using, in IBM's case, this CAPI protocol, and it'll use virtual addresses. It'll actually check the CPU caches, so the data could be in the caches. It'll get the most recent copy. If it's not there, it'll get it from main memory. So it behaves much more like a CPU core. That's the way CPU cores communicate with each other. Send virtual addresses, get me the data from your cache if it's there. If not, I'll go to main memory. So the idea of this is that you could have more fine-grained cooperation. You don't have to send such big chunks of data to cover the latency. You don't have to copy data somewhere and lock it down. I would say so far it's not clear if people really need this. Okay, so it's kind of nice to have. And the CXL standard is one that Intel's gotten a bunch of people to sign on to. So maybe it'll be more widely used over time. But in my own research group, we tried using CAPI, and it worked. So it wasn't like the interface didn't work, but in the end, it didn't really, on our application that we're accelerating, didn't bias much over PCI Express. So I guess the question is whether these interfaces that would allow more fine-grained data communication between a CPU and an FPGA, are there applications that actually kind of need that, right? Where that makes sense. And I'd say it's unclear, right? I haven't seen any killer applications for this yet. So maybe this kind of communication is the future, but it's not clear. The only reason you wouldn't use it is if it costs, is cost. Okay, you did add something, for example, to the processor here. Like this is IBM, it's a Power 8 processor. They had to add hardware support for CAPI. Data comes in through this CAPI port over PCI Express. It actually can ask questions of the cache, etc. On the FPGA side, you typically wind up putting in a little virtual memory to physical memory translation, right? So because maybe the processor asks you a question. So if you want to fully implement it, you also wind up with some extra logic here. So it was soft logic in CAPI. Now you could choose to harden it, but it's kind of until it's very successful, you probably won't harden it. I'm not sure about CXL, whether Intel has hardened some of that. So I agree with you if there was no cost, but there is some amount of hardware cost. Okay, so let's take a break there till maybe 5:36. I'm going to rip you off by 2 minutes on your break. So. Yeah.
So I mean, the first thing I actually want to ask about was, like I mentioned before, quick stuff load, but I've put quite a bit of time making my CNN accelerator.
or the first one you saw here, Catapult 1. But they priced out, I can't remember if I mentioned this already, they priced it out by looking at the web prices, assuming a standard discount on Xilinx Spartan parts, and they concluded it wasn't economic. And it was only years later when they actually went to either Altera or Xilinx and got an actual price quote that they realized the real price was much lower. So it was like kind of the downside of this non-transparent pricing, that for quite a few years, the FPGA vendors made what could have been a very major customer go away because they were sort of, their list prices are so inflated versus what they really charge. And another reason that Intel or Altera got this design win instead of Xilinx, it's not the only reason, but one of the key ones apparently is Microsoft needed another feature in PCI Express that wasn't in the IP cores from either Altera or Xilinx at the time they needed it. And they asked both companies to do it, and Xilinx basically said, you know, we're not going to get to that. Andrew said there was actually an intern from U of T. Well, actually, I'm not sure it was U of T or Waterloo, but it was an intern at the Toronto site of Altera who basically said, oh, I can do that, and he got it back to them in 3 days. And they were kind of amazed by this, that Xilinx has said, you know, can't get it to you, and then an intern in the Toronto site got it to them in 3 days and apologized that it had taken him 3 days. He was like, I was pretty busy, I'm sorry that this took 3 days. And that was a factor in like the fact that they went with Altera. So I don't know who that intern was, but Altera should have given them a giant bonus, right? So, what's that? Yeah, so there's some unnamed intern who made a big contribution to that project. So, okay, so I'm going to switch gears now, talk about deep learning and FPGAs. And kind of, there's lots and lots of papers on this, so I can only do like kind of a smattering of it. So I'm going to give you a little bit of background and preliminaries on DL. How familiar are people with DL? How many people go, I know a lot about DL? Okay, how many people are like, I know very little about DL? Okay, a reasonable number, so it's pretty split. How many people are like, I'm kind of in the middle, I know something? Okay, I think the remainders are like, I've gone to my happy place, but that's fine. So I'll give you a few preliminaries, but it's a big topic, I can't go into too much. Deep learning is obviously going to everything, right? So fraud detection on credit cards, detection of anomalies in medical images, you know, home speakers and voice recognition, robotic guidance in an Amazon factory, self-driving cars and driver assist, etc. So it's all over the place, all sorts of different deep learning models. So the part where FPGAs can play in this, it's not everything, but basically where energy efficiency and latency are important are good markets for FPGAs. And let's take a look at like the embedded market. So clearly if you've got like some little widget that's got a little bit of deep learning in it, then energy efficiency is going to matter a lot. But even for big things, energy efficiency matters. So that's a Chevy Bolt, an electric car. And based on its, its stats, it consumes an average of about 6 kilowatts in the city as it's driving. Okay, that's what determines its range in the city. NVIDIA's self-driving, well, so they don't call it self-driving cars, driver assist system that they recommend you buy, put in the car, put your algorithms on top of, consumes up to 750 watts. Now a car can do that, right? It's got a giant battery pack that actually runs the motor. And it's not catastrophic, but what's interesting is this is actually significant, right? Like this driver assist board will actually noticeably cut your range. Not catastrophically, maybe 10 or 15%, but enough that that's annoying. I mean, car manufacturers put a lot of effort into trying to optimize range. So energy efficiency matters even in something with a big battery pack like this, because deep learning models can be so energy intensive. And even with this very powerful board, we can do driver assist, but we can't do actual full autonomous driving. So there's the need for even more processing. Something else in this application and many others is latency matters. So how many people know what batching is? I guess I'm going to describe this in a few slides. So some know, many don't. That's okay. There's a technique to make your hardware more efficient where instead of asking it to make one decision on a set of machine learning inputs, or like an image, for example, you actually batch up a whole bunch of images and send them all in at once. And that allows you to bring the weights from memory once, use them for a bunch of images, then get some more weights, use it for some more of the processing on all those images. Basically keeps your compute units fed from memory more efficiently. It's a good technique. GPUs love it, but it's not very compatible with low latency. So let's take driver assistance. You got cameras that are recording what's going on around you. And if you're batching, what it means is you actually take 30 images, for example, and send them all to the hardware saying, do you recognize any pedestrian objects? And you will get back an answer after some number of milliseconds saying, yes, I found a pedestrian in every one of these 30 images, but you've already hit the person, right? So it was a very efficient use of your hardware, but it's too late. So in low latency, you don't want to batch. What you want to do is as soon as a frame of video comes in, you send it to this hardware saying, find me the pedestrians. Next frame comes in, send that as well. Gives you lower latency, but it's harder for the hardware to make that efficient because yeah, it has to bring in the weights from memory more often. This is a data center. And I already told you that power is around 30% of the cost. You get wildly varying estimates of how much power data centers take, but everyone agrees it's a lot. So this particular estimate says 6% of global electricity demand could be in data centers by 2030. I personally don't think that'll happen. The reason I don't think it'll happen is that's what pushes people to put in accelerators and so on. You know, so you have to be careful about a straight line curve. But if we didn't make progress, that's where we'd wind up with. I just think we will. Now, in this case, some algorithms that run in a data center, you go, well, do we really care about latency, right? If you're classifying cats, you're scanning the whole internet and you're basically categorizing images for later searches, you don't care about latency, right? Like that's going to take you hours, it doesn't matter. But there are some things, for example, well, I'm going to show you another Microsoft paper where they basically have very tight latency budgets on their machine learning algorithms because people are interactively typing prompts and they're cascading these algorithms. They don't just take one algorithm and run it. Their developers will take this algorithm, feeds another one, is ORed with this algorithm. If every one of those algorithms has very low latency, they can cascade 50 of them together and the end result's still usable. If they have kind of moderate latency, then they can't do that. So some data center applications also like low latency. Okay, so we already talked about this. That's what a CNN is. There are a bunch of different machine learning algorithms, but basically one of the accelerators I'm going to show you does CNNs. So that's what a CNN looks like. Another one is for sequence processing. So CNNs are basically for image classification and object detection. That's generally what they're used for. There are other classes that are basically sequence processing. So some of those are what are called recurrent neural networks, which have now also been are less popular than transformers, which is a different variation on the sequence processing and large language models. I'm not going to go through the details of it, but basically they'll do things like sounds to text, words to meaning, prompts to output, etc. And this is stolen from another Microsoft paper. The only point here is that I'm trying to make is that convolutional neural networks are compute bound. Okay, so because they use these convolutional filters over and over again on a bunch of input data, they have a reasonable amount of data, but they have much more computation. Okay, so they tend to be dominated by compute. A lot of the sequence models are basically more balanced. They have a significant amount of compute, but they're kind of fundamentally doing matrix vector multiplication, and hence they're more balanced in terms of memory and compute, and they become more bottlenecked by memory bandwidth. So we kind of have different neural architectures that have those characteristics. And I guess I already talked about this. So basically, one of the ways that you can get better utilization from your hardware is to increase the batch size. So send a whole bunch of inputs in and get to reuse the weights that you bring in multiple times. But the downside of that is your latency goes up as you increase the batch size. So Microsoft in particular said that even in their data centers, they would really like to have hardware that can produce high efficiency at low batch sizes. So that would be their ideal, right? And then they get best of both worlds. Okay, so that was an extremely fast overview of like kind of the deep learning landscape. So let me talk kind of broadly about strengths and weaknesses of FPGAs for deep learning. Okay, so the first strength is variable precision. This is just a picture of an adder. If I want an n-bit adder in an FPGA, roughly I need n LEs. And if I want an n-bit multiplier, I need roughly n squared LEs if I build it in the soft logic. Why is that interesting? Because deep learning is tolerant of low precision. So, how low you can go varies depending on exactly what your neural network is and exactly what you're doing. Sometimes you can go all the way down to 1 bit, sometimes 4 bits, sometimes 6, sometimes 8. But you very rarely actually need things like 32-bit floating point. Okay, so small precisions work well, and FPGAs are kind of unique in that their hardware gets more efficient as you make the precisions smaller in a very smooth way, okay, at least for the logic fabric. So you don't have to pick from a limited library of, I have these precisions. You can also do very custom things. And I'll talk a little bit later about some custom things Microsoft has done where they've made just unusual low precision formats. So it's not just that you use fewer bits, you can also just kind of do unusual formats in an FPGA, and for deep learning, often that's a big win. So that's one strength. Another strength is this spatial computing style in terms of energy. So as we talked about earlier, you can reprogram an FPGA to do exactly what you want. You can have local data storage streaming between different units. And how much can you gain from that? Well, I don't answer that on this slide, but I give a related piece of information. This is from a talk that Mark Horowitz gave. It's a 45 nanometer CPU, and it's showing where does the energy go. Now, this is a hard CPU, okay, so it's built with ASIC gates. But what's interesting is very little of its energy is actually going to the compute. Almost all of it is going to moving the data around, figuring out what I'm supposed to do, et cetera. So it takes 25 picojoules for this one instruction, which is basically doing an addition. Okay, so they do either a 32-bit addition, floating point, or an 8-bit integer addition. So they do this twice. A 32-bit floating point addition takes 0.9 picojoules, so not much, and an 8-bit integer addition takes much less, 0.03 picojoules. So the energy for the computation is pretty small, especially if you're using low precision. But then you go, well, what else is going on? To get the data from the instruction cache is 25 picojoules. To get the operands from the register file is 6 picojoules. And control logic that decodes this, sets up all the muxes, et cetera, is bigger still. So they wind up with a total of 70 picojoules of energy to actually do somewhere between 0.9 and 0.03 picojoules of computation. So if you can make customized hardware, you can avoid this. Now, FPGAs are going to take an energy hit from the fact that the hardware is programmable. That means your wires are longer and more capacitive, but it's nowhere near this big. Does that make sense? Now, processors can also, like if I did SIMD, I can kind of amortize some of this. So there are things that processors can do to be somewhat more efficient, but these numbers are, kind of shocking to see how much energy is involved in just figuring out what an instruction means and in moving your data around. So there are big wins if you don't do those things. Okay, this is a weakness. So I mentioned this before, programmability is not free. How much bigger is FPGA logic? Well, for the logic elements and the programmable routing, we talked about this last week, but 25 to 30 times larger, 3 times slower. So that's a big hit. One of the ways you mitigate this is try not to do everything in the programmable logic. You have things like DSP blocks that are roughly as efficient as doing them in an ASIC in a custom chip. Although as you use those DSP blocks, you kind of lose one of the advantages of the programmable logic if I could do any precision. Now you can only do the precisions the DSP blocks can support. But there is an architecture opportunity here. Well, there's probably a couple. One of them is these logic elements were designed mostly before deep learning. Can we make them more efficient for deep learning? We know we want to do lots of small multiply accumulates and a few other operations. Maybe we can make these more efficient. So that's one opportunity. Another one is these DSP blocks also were largely designed before deep learning. Maybe we can change them to make them more efficient. Yes. So and some of these slides I stole from a tutorial that we gave at FCCM. But yeah, if you want to know more about this, you go look at this paper. I mean, I'm biased, but I think obviously that They think the conclusions are valid. So I'm not going to tell you what the conclusions are, but it turns out there are ways to make the LEs more efficient. So, okay, another strength of FPGA is massive parallelism. So recent devices, you have tens of thousands of multipliers in the DSP blocks. You can make tens of thousands more in the logic fabric. I guess I just mentioned this. Those DSP blocks were historically designed for signal processing of things like wireless base stations. So they haven't been optimized for deep learning precisions as much. So there's an opportunity there, which people are exploring, academics and companies. But the chips won't be static. Now, FPGAs aren't the only thing that can be massively parallel. I mean, a GPU also is massively parallel. So this is not that's an advantage only for an FPGA. Another strength is flexible memory. So you have tens of thousands of RAM blocks on an FPGA, and you can construct them with the programmable routing and logic into basically any custom memory system you want. So you could make it, maybe I need a lot of weights, but they don't have to feed a very wide data path. Maybe I have a lot of different independent data that I need to access in a very wide data path. Maybe I need to access very wide data words, but I don't need independent access. You can kind of build all those things. So you have a very flexible memory subsystem. And a lot of papers have shown that deep learning is tolerant not just of low precision, it's also tolerant of sparsity. Sparsity is where you basically zero out a lot of the weights. And if your hardware can skip those zeros, you can now gain efficiency. But a lot of hardware can't skip those zeros efficiently. Okay, it's actually difficult in a GPU, for example, to skip over those zeros. If you start putting a bunch of, like for example, you put a bunch of if statements in to try to skip over the zeros, it's actually better to just multiply by 0, right? You'll be more efficient. It's not trivial in an FPGA either, but the fact that you can build these custom memory systems can help you try to exploit sparsity. So you've got a lot of bandwidth, a lot of flexibility on chip in how you build your memory architecture. That's very useful, especially if you can keep all the data on chip. So if you can get all your data on chip, you can really leverage these custom memory systems. What GPUs do instead is they tend to use batching a lot, okay, to keep all their compute units fed, try to bring in multiple inputs and kind of bring in a few weights at a time. A challenge here is that's fine for CNNs, for example, that are going into cars. It's not very realistic for things like large language models, right? So ChatGPT is enormous, doesn't even fit on one chip. Once you get to such large models, they need lots of off-chip memory, which kind of weakens this advantage, right? Most chips have somewhat similar off-chip memory architectures. So it's not really a weakness of FPGAs, but it's no longer a strength at that point because you're all using similar off-chip memory. I'm not going to talk about this in the course, but there are interesting papers that say, well, if I have tens of thousands of these memory blocks on my chip, if you actually look deep inside a memory block, when you're doing reads and writes, there's actually extra parallelism happening. So if you could do a little bit of computation in the memory, as a simple computation, could I do multiply accumulate? You can actually increase the compute density of your device a lot. So that's called compute in memory. You also get rid of all your data movement. It's all being done in memory. The challenge with compute in memory historically has been you make a special memory block that can also do multiply accumulate in some tricky, usually analog way. So you actually are using the analog nature of the memory. And then once you get the answer, you go, now what? I did a multiply accumulate, but now how do I combine this with other things? In an FPGA, the now what's kind of obvious. You have tens of thousands of these memories. If they all could do a little bit of multiply or a lot of multiply accumulate, you let the programmable fabric and the programmable routing do the rest. The max pooling, any kind of other logic. So there are a few papers that are exploring this. It's kind of, compute in memory is kind of risky research, something that people have looked at for a long time. It's promising from an energy efficiency point of view, but has been difficult to make general enough to get a big win, but I think it's a natural fit to FPGAs because you have tens of thousands of memory blocks surrounded by logic and routing. Okay, and the last thing about FPGAs and deep learning is don't forget the IOs. I told you at the start of the course, IOs are a big deal, a lot of area. So deep learning is not just going to, let's think about what that does. So in the data center, the fact that you have very low latency I/O, like the 100 gigabit Ethernet, for example, with hardware on both sides of it, lets you do things like split a large neural network across multiple chips, and they kind of behave like one chip. So Microsoft has done this. My research group has done this. This is a CNN that we split up into a bunch of FPGAs, and basically work just as well as if we had one giant FPGA. More unique still, because GPUs can do things like this too. They work even better in FPGAs because we have so much control over the I/O. Something that's harder for other devices to do is embedded deep learning. So let's say I've got my anti-lock brakes. I have some custom sensor that tells me, when my disk has locked up. You have some custom I/O to talk to that because it's a unique sensor. I have some pre-processing to do that is also somewhat unique. Then I have some deep learning, and then it's going to drive some more custom I/O to drive like an actuator, like my brakes, and pump them. As long as you can do this reasonably, right? You don't have to be like the absolute best. An FPGA becomes the best option for this system. So deep learning is not going to be all of many systems, but it'll be a part of them. So you want to be good at that part, and that fits well with an FPGA taking the whole system. So this is going to be another big market, or is a big market for deep learning on FPGAs, rather than saying it's just this one algorithm that everybody knows. Does that make sense? Okay. All right, so if I was to summarize this, so FPGAs like low precision. So if your network is going to use 4-bit, 3-bit, 6-bit numbers, that's good. If it's going to use 16-bit floating point, that's not as good. If you use sparsity, okay, so a bunch of your weights are 0 and you want to skip over them, FPGAs are pretty good at that because you can design custom hardware that does that for you, and it's harder to do in other devices. If your latency constraint is tight, that's useful because FPGAs haven't needed as much batching as GPU to get performance. Yeah?
When you say like take advantage of sparsity and the weights being 0, but do you mean like when you're physically stamping out like the neural network, you just skip those connections because you know at that point that they're 0, or do you mean like at runtime?
I'm thinking of the ones at runtime where some of them are 0 and you actually steer the data to skip those. But there are a lot of ways to take advantage of sparsity. If you can remove like entire large parts of the network, then usually that's something that most devices can handle, right? Like just the network got way smaller, but in a very structured way. Maybe I removed entire feature maps and so on. It's where you have more unstructured sparsity, if you're able to just take a lot of your weights and threshold them to 0. They were small already, you make them 0, you keep training, the other weights adapt, and it turns out your accuracy doesn't change. So that's a pretty common result, that I can force a lot of my small weights to not be small, but be 0. And with a little more training, I can't notice the difference in accuracy. But if I did that in an unstructured way, just saying I'd want to do that to weights all over the place, and I got rid of 60% of my weights, but they're in sort of an irregular pattern, most compute hardware has a lot of trouble with that. Like they're like, well, what are you going to do? Put all sorts of if statements in? It's probably faster just to multiply by 0. Does that make sense? Yeah. It's not trivial to do in an FPGA either, but because you have hardware for muxes and so on, you can make accelerators that skip over it better. Does that make sense? Okay, so network size. FPGAs, in my opinion, they benefit from not the hugest networks. Because as I said, once you get to really big ones, a lot of this becomes about off-chip bandwidth and how you combine multiple chips. Neural networks are used in 2 ways. So inference is when you've got a neural network, it's been trained, and you want it to make decisions. You want it to recognize pedestrians. That favors FPGAs because it usually is done in lower precision, and you often care about latency. In training, you need higher precision, okay? Because you're still adapting the weights, you're doing the computation at higher precision, and you don't care about latency at all. It's going to take you like hours to train this. You don't care about the latency of any individual operation. So there are some people who looked at FPGAs for training, but I think it's a tough sell. I think a GPU is essentially, and a Google TPU, there's a reason that they've been architected the way they have. They're very good at this. So, and then the other thing we didn't talk about much is programming model. So if you're going to deploy a neural network in an FPGA, some of the accelerator styles that we're talking about, well, if you don't update the network very often, that's good. Because an FPGA is harder to reprogram. It's a harder design style. So if their network is changing really often, that's harder. If it's changing less often, I mean, it's still not really a strength to be harder to program, but it's less of a barrier. And we're going to talk about a couple of accelerator styles, like ways you can organize your computation, and some of them are easier to update than others. Does that make sense? Okay, so I'm going to pause here for a second. Am I going at a rate that is just killing you, or is this fine? You're good? Anybody else? Isidore's with me, but is everybody else lost? I had one prof when I was in grad school who would periodically ask that same question, am I going too fast? Everybody would say you're going too fast. He would slow down for 4 minutes, but then he couldn't take it. He'd go fast again. So, so I'm going too fast, tell me. I won't be offended. Okay, I'm going to take that as no. Okay, so that was kind of an overview of like where are strengths and weaknesses there. The reason I find this interesting is because deep learning is going into so many systems. As I said, it'll be part of a huge number of systems. So as a person who architects FPGAs, you want to think about how can you make them better at those systems. So I think that's a major question. So now though, let's say we've got an FPGA, we've decided we're going to put part of our application's deep learning, we're going to put it in here. How could we do that? So the first engines that tried to accelerate neural networks on FPGAs they basically just took a part of the neural network. They did part on the CPU, they did part on the FPGA, so they would offload maybe just the convolution or maybe some matrix multiplies, and they'd leave other things, maybe max pooling, the fully connected layers on the CPU. And they basically weren't very general. The reason they're not very general is they tended to be handwritten, so somebody made a bunch of Verilog to do this. And they also weren't that efficient because they'd be bottlenecked by the CPU. You weren't doing the whole network. The next sort of set of designs that went into FPGAs were model-specific accelerators. So they took the whole model, the whole neural network, or at least all the compute-intensive portions, and put it on the FPGA, so they got a better efficiency. Okay? They're still not very general, because they accelerate one neural network. Somebody worked for many months anyway, usually, to create a hardware design that could accelerate that network. And if somebody changed it, they came up with a better network or something else changed, you can't use that one anymore. Okay, so your design cycle was very long. So another style is basically take these model-specific accelerators and automate their creation. Okay, so you still want an accelerator that does only one model. You're pretty sure you're deploying it, but you also aren't sure the model's frozen yet. Maybe it's going to keep changing. So you make an infrastructure that, given a TensorFlow or PyTorch input, can produce the accelerator. And there are a few different infrastructures like this, commercial and academic. They're basically domain-specific compilers. They don't try to do everything. They know how to do a certain kind of neural network. You give it that description, they will stamp out the right hardware for it. Give it something else, it has no idea what to do. Okay, so it is easier to make this efficient than to make a general high-level synthesis tool efficient. And then the last kind are overlays. Okay, so overlays are software programmable. So you've got a very, very weird, very highly customized, very parallel form of soft processor. And it can be programmed by some special compiler with its own instruction set. But because it's such a weird processor, it's quite efficient for neural networks, although usually not as efficient as the custom hardware. Okay, so you've lost some, but you've made it easier to program. Okay, and the dominant ones are these now, right? These are the two styles that people typically use because you just need like a flow that makes you more productive. Okay, yeah, and they're balancing how efficient they are versus how easily you can program them. Okay, so I'm going to show one example from each of these two things. And they are selected from my group because I know them well. But they are also actually the highest performing version of each of these things, right? So they're also selected for that reason. So it's not a completely random choice either, although it obviously makes it easier for me to speak about too. Okay, so the first one I'm talking about is H-pipe. which stands for Heterogeneous Pipelined Accelerator. It also turns out that it also represents a certain exhaust pipe that you can put on your car to make it louder and more obnoxious. But we didn't know that when we chose the name, right? So it stands for Heterogeneous Pipelined Accelerator. Okay, so the design philosophy of many accelerators on FPGAs is you build a whole bunch of PEs. Okay, so you build some general processing element, and you put a whole bunch of them in parallel. So maybe they're SIMD, maybe they're organized in some other way. And a neural network, in this case, we're targeting convolutional neural networks. You could take every layer in that neural network and basically say, okay, let's map the first one. This is a two-dimensional convolution, 7 by 7 filter size. Stride 2 means skip over 2 pixels each time. And we're going to map that onto this PE array, compute it in parallel. We're going to store the output in some buffer. And then we'll basically move on to the next layer. Okay, so the next layer is going to take its input data from this buffer. We're going to have these PEs do something different, and so on. So we'll kind of go through kind of temporally, right? Like layer by layer, saying, use my array of PEs to compute what that layer needed, store the temporary results, now move on to the next one. And there are a lot of FPGA accelerators that do that. Yeah?
Doesn't this necessarily require really big buffers? Because like if you could space, if you could do like streaming compute, then you could get away with like not storing any of that.
Yes, so this needs a buffer that's big enough for all the output of that layer. So it depends, so this fits CNNs reasonably well because their output data isn't as big, but sometimes this output data might overflow the chip too. So you might have to spill it to main memory, which is going to cost you some efficiency. And you're right, you have to be able to store the whole output, and that becomes the whole input of the next layer. But it does allow you to kind of micro-optimize, like design this PE and HDL, and then essentially just design the control, right? Often instruction control to go through each layer. So that's a pretty common approach for accelerators. That's not what HPipe does. It's a data flow accelerator. So it means that it basically builds a custom PE, so it's not a generic one that can do anything. It builds a PE. This PE could only do a 7 by 7 convolution. This PE could only do a 5 by 5 convolution. This PE could only do 3 by 3, and then there might be a max pool and so on. So every PE is different, and it only knows how to do one thing. And they are directly wired together with a small amount of buffering. So this is more of a streaming style, and the PEs are all different and customized to the network. This looks like a pipeline, and you can pipeline it really deeply. So I'm going to show you exactly what we do. But basically, yeah, this can get very efficient performance on an FPGA. Yeah?
One thing though that does come to mind about the relative, these two approaches. Wouldn't the second approach, like it's great if you can fit it on chip, but it's a lot more likely that you're going to overflow your chip with a really deep network if you just can't fit, an individual PE for each, network layer. Whereas the first approach, you can basically fit an arbitrarily large network.
Yes. Yeah, that's a good point. So we do need a minimum number of PEs here because they're all different. We need at least one PE for each layer. Now these PEs are parameterizable. So basically their amount of parallelism can be changed in the compiler I'm going to show you. So it can scale them up, scale them down, but you're right, there's a minimum. Once it's scaled it down to the minimum, it still needs one of each. And that means if you were trying to go for the smallest chip and you didn't have much throughput needs, this might be a better approach. So that's a good question. So this is actually, for that HPipe compiler, this is like the floor plan of a particular neural network, MobileNet V1. This is doing object detection. So the plus SSD means plus single shot detection. So this isn't just classifying images, it's detecting objects and saying what each one is. So it's be like things like pedestrian detection. The input comes in here. So that's where the images are coming in. And I forget where the boxes are going out. But basically, you can actually see the colors are different layers. So all that's supposed to show you is there really are all sorts of different PEs. Some of them are bigger and some are smaller. Depends on the complexity of what they're doing and how much throughput you need from that layer. So the compiler does assign different amounts of hardware to different layers. And the data is kind of streaming through in some irregular way, right? Like the tools have decided how to lay it all out, but it's flowing through this whole accelerator. Let's see. And I guess it's an interesting example of compute models. So each of these PEs is very deeply pipelined, and it's deeply pipelined with just basic pipeline registers, okay? Like not what the most simple data flow model we looked at, right? The single rate synchronous data flow. In between the PEs, it basically uses ready valid signals and FIFO buffers, okay? So it's using the more flexible, you can have data rate mismatches, you can have bubbles, et cetera, but only in between the PEs where we basically can't quite figure out all the latencies. All of that can be run very fast because you can pipeline very deeply, and we only pay for the FIFOs at kind of the coarse grain between layers, and within a layer, we use the more efficient, just basic pipeline registers. So kind of combining those two compute models. And yeah, the downside of this is it needs a new, you need new hardware for every model. So you change that from MobileNet V1 SSD to MobileNet V2 SSD, and you need a new compile. And you'd actually have to go write all the hardware if you didn't have a compiler. So these style of accelerators typically need a domain-specific compiler. This is the one for HPipe. Basically, it takes in a TensorFlow graph that is the neural network, takes in limits on your hardware. So you say, what's my hardware budget in various resources? Basically optimizes the graph, decides where to allocate resources, and then generates the RTL. And the generating RTL, it basically has all sorts of templates. So the way it generates this RTL is there are a lot of late nights of grad students who wrote the templated RTL, and this now can connect that templated RTL together, rather than it's trying to figure out its own RTL. Let's see if so this animation is just basically showing the compiler in this case had a budget of 5,000 DSP blocks, and the way let's see if I can go back and do this again. Okay, so it basically starts by just giving the minimum number of DSP blocks to every layer. And certain layers have higher latency when you do that because they have more compute. So it gradually assigns more and more DSPs to them, increases their parallelism settings until it basically balances the pipeline, right? The throughput of this pipeline will be limited by the slowest layer. So it allocates resources to try to match the throughput of every layer. And until it runs out of DSPs. And usually what it runs out of is DSPs. Let's see. I'm not going to talk too much about this. Basically, I guess I already talked about most of this. This is how the domain-specific language works. I don't think I'm going to talk about it too much. The compiler also takes into account a lot of physical characteristics. So to make it really fast, it actually is predicting how long the interconnect delays will be and therefore how deeply it needs to pipeline. And even whether it should broadcast things in trees or put them in chains and so on. So it's kind of aware of how it has a good guess of how it's physically going to be implemented, and therefore how much it needs to pipeline. Okay, so how does this work? So this is HPipe. It basically works at batch one. It doesn't need to batch up images. You just you get an image, you send it in right away. And it gets a very low latency, about a millisecond, and it can process about 5,000 images per second. If we compare to a same generation GPU, the GPU, which is a high-end GPU, it's actually a bit bigger than this FPGA, at the same latency, it has a lower throughput by a factor of about 4. If you start batching, it will get better throughput, but it'll have worse latency. And if we kept increasing the batch size, it'll actually go up like this. It'll actually exceed the FPGA's throughput, but at a higher latency. That was the results on kind of a classic FPGA. After that paper came out, sometime after it, Intel released an AI-optimized FPGA. What they did is they changed the DSP blocks to be better at low precision. I'll talk a bit about this later in the course when we get into DSP blocks. But they're harder to use to get a lot of multipliers in. They basically put more restrictions on them. But if you could live with those restrictions, you could get a lot of small multiplies, which again, in neural networks, small multiply accumulates, like low precision can be okay. So it required a bunch of re-architecting of this, but at that point, the throughput of this goes up a lot, and now it has a better latency than a GPU and a higher throughput, kind of no matter where you choose the points. So I guess the point of this is data flow accelerators, can be very efficient. One limitation of this, H-pipe needs to get everything on chip, right? So if you're taking a really big network where you can't fit all the data on chip, then it's not going to work that well. And the GPU will also suffer, but probably not as much. So that's kind of, again, smaller neural networks probably are ones that fit FPGAs well now. I mean, these are big CNNs, but those are smaller, much smaller than large language models. Okay, so that was a data flow style accelerator. Is everybody with me so far? Okay, so this is like your deep learning crash course. Okay, so let me show you an example of the other style. This is a collaboration with Intel. So this paper is by both Andrew Boutros, one of my PhD students, and Intel. So this is the other way you can try to be productive with FPGAs, overlays. So the traditional flow, you got a bunch of applications, you implement them in RTL, the CAD tools are kind of slow, you check your performance and optimize, eventually you're happy and you get bit streams. And you need multiple bit streams because you had multiple applications you wanted to support. The overlay flow essentially separates the hardware design from the application developers. So the hardware experts have to think about, what do we need to accelerate kind of all these applications? What would be a reasonable processing engine? They have to basically decide, okay, well, what kind of data path would I make, and what would be the instructions that could control that data path? And then they have to build the hardware writing it in HDL usually, maybe in high-level synthesis, but usually in HDL because they want a lot of efficiency. And they also have to develop basically a software tool chain, like something that allows you to take some input description and turn it into the instructions that will control this. So the hardware developers have a lot of work to do. But once they're done, the application developers, so with neural networking, these are data scientists and so on, they can basically just write software, right? They write software, it goes through this overlay compiler, produces instructions that very quickly can run on the FPGA. So they essentially don't really notice that it's an FPGA. It's just something, right? It's a black box. They send in instructions and out comes data. Yeah?
In order for this to be effective, though, I would assume that the application developers still need to, at the very least, be aware of the kind of parallelisms that work well on the hardware they're targeting.
I guess it depends on how good your software flow is. I mean, I guess part of it is you would generally target some set of applications that are not as broad as the whole of machine learning. Because if you targeted the whole of machine learning, then you're probably going to wind up going, hey, I should make a GPU. But you probably don't want to do that because NVIDIA already did it. Does that make sense? So you're going to narrow it some. So there's probably some constraints on them to begin with. I only care about you guys, not everybody else. And you're right. Whatever you put in your software compiler is going to affect how carefully you have to write it. So if your software compiler is more primitive, they're going to have to think more about what can it do well and what can't it. And it probably is going to be more primitive. Again, a lot of the competition in this is going to be NVIDIA, which has spent a long time improving their software compiler. So you're going to have to gain something significant by specializing to these application developers. Otherwise, it's probably not compelling. Does that make sense? And there are cases where it's not going to be compelling, but there are cases where it is. Okay, so this example this is called the neural processing unit. I'm not going to go into the details of it, but basically it's just kind of interesting to see what is one particular overlay look like. So this is a handcrafted data path in RTL. It's basically a big matrix vector multiplier, and then two different wide vector units, so SIMD units with a parameterized but typically quite wide, like 32, 40 way SIMD, and then a load unit. Most of the units are chained together. Okay, so generally they're not getting their data from registers, they're just getting data from the previous unit. And the reason is it turns out deep learning is pretty friendly to that. This kind of deep learning model, this one is really targeted at those sequence models, tend to have a matrix vector multiply followed by a whole bunch of operations that you can do in SIMD, followed by store it back and send it again. So you get rid of a lot of register file access by just saying I'm not going to allow it, right? You must go to the next unit. It's fundamentally always SIMD, and the first part of this is beyond SIMD. It's actually matrix vector multiply. So it is controlled by instructions, but a single instruction can execute 45,000 operations. So that's how it gets efficiency. It's amortizing that instruction to code by a huge amount. Does that make sense? The memory subsystem is all embedded throughout this. There's basically the right amount of registers. As I said, there's a cascading of operations rather than accessing it from register files in many places. So how well does it work? So this is a comparison to same generation GPUs. Okay, so it's a T4 GPU and a V100 GPUs. V100 is very high end, T4 is a bit smaller. And then this neural processing unit. They're all in the same process technology, and the FPGA actually has the smallest die size. So this is kind of trying to do a fair comparison. Higher is better. This is basically how many inferences you can do. And over a bunch of different sequence models and matrix vector multiplies and so on, the FPGA does very well, okay? 11 times faster than a GPU that's bigger than it. Yeah?
I'm not sure if I know the answer to this, but I know like with the new Apple, with the M1, the M2, they keep advertising like neural unit. Is this what they're talking about?
It'll be their own neural unit. So I mean, neural unit, neural processing unit is a very vague term. So the NPU means that's the name that this project has. They have, so I don't know the answer, but my guess is that it is pretty common to have some kind of matrix vector unit and some SIMD units. So my guess is it won't be the same. Probably more general because they can't just go reprogram it, but some of the same ideas probably show up in it. Does that? That's probably, I can't give a more detailed answer without knowing more. Okay, so now this overlay is targeting certain, we're testing it on the things it was designed for. Okay, so we're not testing it on things it wasn't designed for. In fact, you can't even do them. But on the things it was designed for, it works well. That was compute. In the end, when you put this in a system, and the system that we're thinking of for this one would be in a data center, where the data is coming in over Ethernet, you're processing it, you're sending it back. This is basically execution time, so lower is better now, and it includes the time to get the data there and get set up. So compute is the biggest thing. So that's the, well, let's take the V100. So this is the V100 compute time. And the NPU is much smaller than that. There's also a significant amount of data transfer time, which is also much slower in the FPGA. So that's, again, because FPGAs have these hardware IOs, hardware accelerated networking, and so on. At the system level, it does quite well. Okay, so I guess those are two studies that say that, can FPGAs do well in deep learning? Yes, you can do well with either streaming overlays, where it's specific to the model, or streaming hardware, where it's specific to the neural network, or with overlays. The ease of use is still worse than a GPU. The generality is worse. Like, part of what you're getting is you're specializing more to this network, and that's how you're getting the performance, or this class of networks if it was an overlay. And part of why I'm telling you this is because when we get into like the details of how you architect an FPGA, some of these blocks will talk about how we can make them more effective for deep learning. So it's useful to know what deep learning looks like on an FPGA. Okay, I'm almost done. I'm going to give you a very quick overview of Microsoft Brainwave. So that's the last paper from Microsoft. So the NPU that I just talked about was actually Microsoft never released the code for this Brainwave project, but the NPU is basically inspired by it. Okay, so it's like believed to be a very similar architecture, although Microsoft never released the code for this. So what Microsoft Brainwave was basically another overlay processor for neural networks on FPGAs. I kind of already talked about this some. This is basically part of Microsoft's motivation is they're talking about the latency requirements that have been published. So Google said they needed their TPU to return an answer on a neural network inference in 10 milliseconds for the first generation. When they went to the next generation, they'd cut that time to 7. Microsoft basically said they wanted to hit 4. So the latency budgets are very tight. And I guess I told you why before. because they want to combine a lot of neural models and still have a good user experience. So even though these are going into data centers, they actually target very low latency. And at the time Microsoft published this, they said sequence models were the dominant things they ran in their data centers. So these RNNs and LSTMs and so on. And CNNs were less. And these RNNs and LSTMs use they have a lot more memory bandwidth effects. Okay, I think I already talked about this. So what Microsoft did in Brainwave is they made an overlay. And again, it's like the NPU, but really it's like the NPU is like Brainwave because Microsoft did it first. They basically said, well, okay, we need a lot of memory for these sequence models, or memory bandwidth matters a lot. What if we can get all the memory on chip? If we can get all the memory on chip for all the weights, then we could run really fast. So that's what they're targeting, what they call persistent neural networks, where you get all the weights on chip. Now, how are you going to scale that to bigger networks? Well, they said, we've got this catapult architecture where our data centers all have an FPGA in them. They're all connected by fast Ethernet. If we need to scale to big models, we just treat the whole thing as one giant chip where it's connected by Ethernet. Their compute model is an overlay. They actually use Neos as their control processor, so Altera's soft processor. But they basically augmented it with a giant coprocessor that, again, is similar to the NPU. So I like the NPU figures better, but so you can imagine this is just similar, right? That you've got these matrix vector engines and these SIMD units all combined together. And they can launch even more operations. So I said the NPU could launch, I think I said 45,000 operations with a single instruction. They say Brainwave can launch 7 million with a single instruction. So they're not exactly the same, but they both use this philosophy of an instruction should do a lot. And yeah, this is kind of maybe too detailed. Basically, they're using a bunch of SIMD and then custom units. The SIMD has all the operations you want in these neural networks and nothing that you wouldn't use in these neural networks. So they've decided, they've got a sort of custom ALUs. And then they also want to be good at matrix vector multiplies. So they basically build a whole bunch of units that are good for that over here. And yeah, otherwise pretty similar. One other thing they did that is interesting is they have this result on the impact of customizing your precision. So they started out with 16-bit integers. And let's look at the purple line, because that was Stratix 10, so that's a more recent FPGA. They looked at how much could they put in the chip? How many teraops per second could they fit of multiply accumulates? And for that chip, they could do 12 teraops per second at 16 bits. If they went to 8-bit integer, they could do 31. So there's a big gain to going lower precisions. If they went to a custom floating point, so this is not a standard floating point format. They called it Microsoft Floating Point 9. They could actually go to 65. The reason it's so efficient is they don't have very many mantissa bits. They have a lot of exponent bits. So their multipliers are actually very small. Mostly they have adders of adding the exponents and some shifters. And then they could go to a Microsoft Floating Point 8, which was even better. Okay, so they got a factor of whatever that is, approximately almost 8x by going from 16-bit integers to this 8-bit custom floating point number. So it's much more efficient. And then the other question is, what does it do to accuracy? This is accuracy on 3 different models. Higher is better. The blue bar is floating point 32, which you'd probably never really want to deploy, but it's kind of the gold standard for accuracy. And as they go to these 2 floating point numbers, as they go to the FP9, they lose a very small amount of accuracy on the red bar. But if they retrain a little bit, they get it all back. Okay, so basically they get these performance improvements without really any impact on accuracy, as long as they're willing to do a little bit of retraining. And Microsoft's gone on since this, to publish other papers with even smaller and weirder floating points. So they're continuing to monkey around with exactly how do they represent the numbers. And this is something that FPGAs are very good at, right? You can change your representation to anything, and if you make it smaller, the hardware will get more efficient. So, okay, that's all I had to talk about today. And that was probably the largest number of slides I'm going to show this year. So if you made it through this one, you're over the hump. So, okay, thanks everybody.